Hello everyone. So today we are going to look at the concept of substantial derivative. So for that we need to just look at the symbol that we use to represent the substantial derivative. So substantial derivative is represented by as d by dt. This is for time. This t is for time. Okay, and these are the capital D. So this is the symbol for substantial derivative. So suppose we want to write the substantial derivative of any property. Let's take density. So we can write as d by dt of rho is for density. Similarly, if you want to write the substantial derivative of temperature, we can write as d by dt of temperature. Okay, so this is basically the symbol for representing substantial derivative. Now let's look at the meaning of substantial derivative. Okay, so uh, okay, just I'll take 1 minute to draw the axis. Now this is our coordinate system, and this is x, y, and z. Okay, so suppose we have a fluid element. This, let's take, this is point 1. Okay, this is point 1, and at this point the fluid element has a velocity v1 in this direction. Okay, and v is basically the velocity vector is u I cap, the velocity in x direction, plus velocity in y direction, plus velocity in k direction. Okay, so this is the velocity vector ui cap plus vj cap plus wk cap. Okay, now this particle is moving. So suppose it follows a path like this, and at uh, time t is equal to t2, this fluid particle has come to point 2. Okay, t is equal to t2, it is at point 2. This is point 2. Okay, it was at point 1 at t is equal to t1. Now, and this is again not it has not stopped, it is again has some velocity, and it is going in, suppose in the direction it is going in the right direction. Okay, now this is v1. So, let's talk about density. We'll understand the substantial derivative of density. Okay, to understand the meaning of substantial derivative. So for that we'll assume that this fluid element has a density of rho1 at this point 1, and rho2 at point 2. Okay, now there are two things. As this particle is moving, we can see from the here that its density had changed. Okay, it was rho1 at this point 1 and rho2 at point 2. So there are two reasons for the density to change. Density, the first one is that the density change density can change at a fixed point with respect to time. So suppose to understand this sentence, we just look at the, suppose we have a axis like this and a fluid element we have here. Okay, so as time passes, this fluid element is fixed here. Assume that this fluid element is here, it is fixed. So what this sentence mean is that even if the fluid element is fixed here, with respect to time, as the time passes, its density will change. Suppose at t is equal to t naught, it has a density of rho naught. Then as the time will pass, suppose t is equal to t1, its density becomes rho is equal to rho1. The particle location is fixed, but still the density is changing. Why? Because density is changing with respect to time. Okay, so at time t is equal to t2, its density will become rho2. So this is one of the reason for changing density, that the density is changing with respect to time at a fixed point. Okay, now we are talking about this scenario. So as this particle have moved from here to here, from point 1 to point 2, its density has changed. So one of the reason is the change in density with respect to time at a fixed position. Okay, the other reason can be the density changes with respect to space as the particle moves, as the fluid element moves. Okay, density changes with respect to space as the fluid element moves. What this means is, here suppose let's again draw a coordinate axis. Okay, so suppose at t is equal to t1, the particle was here at this point, and sometime it has moved to point 2. Okay, so due to this movement, its density had changed, because density was suppose rho 1 at this point and rho 2 at this point. So due to the movement of the fluid element from point 1 to point 2 is the reason for the change of the density. Okay, so what we have seen is the density can change with respect to time also at a fixed position, and density can change with respect to space also. Okay, so these are the two reasons for the change in density. Okay, so what we want to say mathematically is that the density is a function of position, and it also depends on time. Okay, this is the meaning, that the density is a function of position and time. So for that, now, okay, so if you want to write rho 1, we'll write rho x1 comma y1 comma z1 comma t1. Then this is the density at point 1. Okay, at this point, this is rho 1 comma rho 1 is equal to rho x1 y1 z1 and t1, and at point 2 it becomes rho as a function of x2 y2 z2 and t2. Okay, now we'll just go through a simple derivation to understand better the physical significance of the substantial derivative. So for that, we'll use a simple theorem called Taylor's theorem. So I'll give a brief understanding about that theorem. So this is f. Suppose we have the value of f at x. We know the value of function f at x. Okay, and we want to find the value of function f at x plus h. Okay, we want the value to be here, to know here the value at x plus h, and we already know the value at x is equal to x. Okay, so for that we have the theorem that f at x plus h is equal to f at x plus h into f dash x plus h square by 2 factorial f double dash x, and simply these terms will continue. Okay, so f of x plus h is equal to f of x plus h into f dash x plus h square by 2 factorial f double dash x, and similarly the series goes on. Okay, this is the Taylor's theorem. Okay, so we'll use this concept here. Now we know, suppose we know the density at point 1. Okay, this rho 1 is known, and we want to find the density at point 2, that is rho 2. Okay, we have rho 1 we have known, and we want to find rho 2. Okay, so we what we will do is, this is at x1 comma y1 comma z1 comma t1, and this is at x2 comma y2 comma z2 comma t2. So what we will do is, basically we will expand this theorem to 3D. So if we expand this theorem to 3D, then suppose we have f, we want to write at f of at x2 comma y2 comma z2 comma t2. I have included the time also. Okay, let's just write it for density directly. So if you want to write for density, that is rho 2, and rho 2 is at x2 comma y2 comma z2 comma t2. So we will use the density at x1, that is rho 1, at x1 comma y1 comma z1 comma t1 plus we'll just take the differences for each axis. So for first we will take for x, that is x2 minus x1, and then the derivative of density with respect to x. Okay, now again we will use y2 minus y1, then derivative of density with respect to y, again z2 minus z1, then derivative of density with respect to z, again with respect to time t2 minus t1, and then derivative of density with respect to time. This is, we have expanded this Taylor theorem to for 3 axis, and also the time axis we have included. Okay, now if we will just shift, do the mathematical manipulation, that is we can write rho 2 minus rho 1 is equal to x2 minus x1 d rho by dx, okay, plus y2 minus y1 d rho by dy, plus z2 minus z1 d rho by dz, plus t2 minus t1 d rho by dt. Okay, now I will just divide by t2 minus t1, t2 minus t1, so it will become x2 minus x1 divided by t2 minus t1 d rho by dx, plus y2 minus y1 divided by t2 minus t1 d rho by dy, plus z2 minus z1 divided by t2 minus t1, okay, and it will become d rho by dz. Then finally it will get cancelled up, so we have left with d rho by dt. Okay, now I will take the limit as the limit delta t tending to 0. Okay, so what this term is, this is basically, we call it as capital D by dt, d rho by dt, and this is equal to, this term is change, this is basically position upon time. Okay, so this is velocity, so this is s component of velocity, so we can write as u d rho by dx. Similarly, this is y component of velocity, we write as v d rho by dy. Similarly, the z component d rho by dw, w d rho by dz, then d rho by dt. Okay, so this is what we have got. Now if I arrange this, then we can write d rho by dt is equal to d rho by dt plus mu rho by dou x plus mu e y w dz. Okay, so this is what we have got. Now as you can see that on the left hand side we have the substantial derivative term and on the right side we have, I have arranged the two terms, one in the bracket and this one is not in the bracket. Okay, so these are basically the two terms. So this is what we call as substantial derivative. Okay, let me change the pen. Substantial derivative of density, and this is the local derivative, and the term in the bracket is called convective. This whole term is called convective term or the convective derivative. Okay, and just again simplification, what we can do is we can represent this whole term as d rho by dt is equal to dou rho by dou t plus velocity times, okay, and then density. Okay, so we can represent this whole term as like this. Now we will understand the concept of substantial derivative from here also, we can understand from here also. So what we are looking here is that a substantial derivative of density is basically the change in density with respect to time and the change in density with respect to position also. Okay, so substantial derivative of any property has two terms. One is the change in density with respect to time, if we are talking about density, the change in density with respect to time, and the change with respect to position. So now we can understand it better. So let me first write the definition of substantial derivative. Substantial okay, substantial derivative. So it is basically the change in the property of a particle with respect to time as the particle moves through the space. Okay, so this is the definition: change in the property of a particle with respect to time as the particle moves through the space. So now we can understand it better here. As this particle or the fluid element is moving, how its density is changing. One is changing with respect to time and other is changing with respect to position. So substantial derivative is the change in property with respect to time as the particle moves through the space. How its density is changing when it is moving in the space. That is what is substantial derivative. How the density of this particle or the fluid element is changing when it is moving in the space. Okay, so that is represented by substantial derivative. We have to focus on this particle. Okay, we have to observe this particle. Just observe this particle. This particle, observe this particle. So at suppose at some instant it will be here. We have our eyes focused on this particle. Just focus your eyes on this particle and just observe it. Now it will come here. Okay, again after that it will come here. So this particle is moving like this, and then its density is changing. One is changing with respect to time at a fixed location, and other as it is moving through the space. Okay, so this is what we have for substantial derivative. So I hope you can understand. uh, Thank you.